Now, coming to the enthalpy of solution. Already we have done the enthalpy of that is reaction, enthalpy of combustion, enthalpy of neutralization. Alright, now we will come to the enthalpy of what you can say solution. So the name itself it says solution. So enthalpy of solution of a substance in a particular solvent is defined as the enthalpy change, that is amount of heat evolved or absorbed, we can say that, when 1 mole of a substance is dissolved in a specific amount of a solvent. When 1 mole of a substance, when it is dissolved in a specific amount of solvent, the amount of heat which is evolved or absorbed, that is called as enthalpy of solution. That is known as enthalpy of solution. Alright, when 1 mole of a substance is dissolved in a given amount of a solvent, in a specific solvent, we can say that. Alright, however, if such a large volume of the solvent is taken, then what you find is that the heat, it is not basically evolved, it is basically absorbed in the solvent itself. The heat is evolved, but it is absorbed in the solvent. For example, you have seen it. That is when we add dilute sulfuric acid to water, when we add concentrated sulfuric acid to water or concentrated HCl to water, alright, to make it dilute. So a large amount of heat is evolved, large amount. For that purpose, what we do is that we add slowly the acid to the water and we take water in large amount. Alright, we take in large amount the water. For example, let us say we take 5 liter of water. So to say, just an example I am giving you. Let us say I am taking 5 liter of water and we are adding 125 cc of sulfuric acid to it, concentrated sulfuric acid, to make it dilute, we can say that. So a large amount of water is being taken, we can say that, to make it dilute, so that whatever the heat is evolved during the course of the reaction is being absorbed by the water, and hence the vessel is not going to crack. Alright, the vessel is not going to explode because a huge amount of energy is evolved, we can say that. Clear? So in certain cases, that is, water is taken, the solvent is taken in a larger amount, so as to what you can say, that is, spread the energy, so as to distribute the energy uniformly, so that the vessel does not explode or no explosion takes place or no accident occurs in this particular manner, we can say that. So hence, in that particular case, the solution which is being prepared when the solvent is large amount, is in excess amount, we can say that is known as enthalpy of solution at infinite dilution. That is known as enthalpy of solution at infinite dilution, because I said you already, that is, a solvent is large, solvent is excess, we can say that. You know why I said that I have to take the solvent in large amount, in excess amount, so to say. Now generally, when there is enthalpy of solution is taking place, means whenever a substance is dissolved in a given solvent, 2 steps takes place, 2 steps. The first is the breaking up of the ions. The compound breaks up into its ions. Alright, that is the first step. Second step, the dissolution of these ions in the given solvent. The dissolution of these ions in the given solvent, that is called as the enthalpy of hydration, also we call it as. Alright, the first is ionization. The next is your dissolution of ions in a given solvent. If the solvent is water, that is said to be as hydration. Also we call it as enthalpy of hydration, so to say. So now this can be explained better by that is an example that is said to be as Born-Haber cycle. Now this was given by Max Born and that is Fritz Haber, we can say that. Alright, Max Born and Fritz, F-R-I-T-Z, Fritz Haber, the two scientists, they gave a cycle which is known as Born-Haber cycle. The Born-Haber cycle says that how a given ionic compound is formed. How a given ionic compound is formed. For example, it is a sodium chloride. Basically, how it is being formed. So first of all, sodium that is solid, we can say that. It sublimes, alright, that is S I am taking for sublimation energy, I am taking it, the enthalpy of sublimation, to form sodium gas, because whenever you want to add an electron or whenever you want to remove an electron, you need to convert it into gaseous state. Alright, for that purpose you have studied in what you can say ionization energy, or you have studied in electron gain enthalpy or electron affinity, so to say. So it is the amount of heat energy required to add an electron to the outermost shell of an isolated gaseous atom. So we need to convert it into a gaseous state. Why? Because once you convert it into gaseous state, the atoms are far apart from one another. So intermolecular force of attraction is the least. So you can remove an electron, you can add an electron to it as well as you can remove an electron from it, because the intermolecular force of attraction is the least. So generally, whenever we are adding or remove an electron, we need to convert it into gaseous state. So we go for sublimation. So then what we do, that is I have to convert into ion, sodium ion, how will I convert? I remove an electron, so that is ionization energy, we can say that. I am adding. So first I am subliming it, I am going for sublimation to convert into gas, then after that with ionization energy I have converted into sodium ion. Done. Now I have to convert into chloride ion. Alright, the chlorine gas also I need to convert into chloride ion. So first that is we will take that is what you can say Cl2. It is going to dissociate, undergo dissociation energy to form Cl. We can say that. Now this is a dissociation energy or decomposition energy, we can say that. To convert into Cl, we can say that. So Cl2 to Cl, we can say. So hence what we will do, we are doing it, we are dissociating into half you are doing, isn't it? From 2 Cl we are making to 1 Cl. So it is half D. D stands for here nothing but the dissociation energy, so to say. Clear? Fine. Now this Cl gas which is being converted, Cl2 to Cl gas. Cl2 is of course a gas, no need to convert into a gas, already it is a gas, just we are dissociating it. Now what we will do is that I am being converting into Cl minus. So Cl minus means what I have to do is that, that is electron affinity I have to give. That means here that is energy will be released for addition of electron. Correct? Energy will be released for the addition of electron from the outermost shell, so Cl minus. So now this particular one, Na plus and Cl minus, now they combine together, that is Na plus and Cl minus, they combine together to form, that is nothing but NaCl. So when they combine together, alright, when they combine together, what happens is that, is the heat of formation, we can say that. Clear? So it is known as delta F H naught, that is the heat of formation, we can say. So it's been taking place because from sodium ion, chloride ion combines to form sodium chloride. So heat of formation is being there because a compound is formed, because I said you already, we cannot form an element, we are making a compound. So compound is formed here, sodium chloride is formed. You can see sodium chloride is formed. So there is some heat of formation. So how much is the heat of formation? That I need to calculate here. How much is the heat of formation? So see here, delta FH naught is equal to, what is that? It is sublimation energy plus ionization energy plus, that is a half dissociation energy, plus electron affinity plus the internal energy which is being present. Alright, all together will give you the heat of formation of sodium chloride. Altogether, it is going to give you the heat of formation of sodium chloride. So when all this energy is present, or suppose you know the heat of formation, you do not know internal energy, you can calculate from here. If anyone is unknown, you can calculate, we can say that. Clear? So in this way, this is known as the Born-Haber cycle. So the important consequences of this lattice enthalpy is that greater the lattice enthalpy, more stable is the ionic compound. Means lattice enthalpy is what? Lattice means definite geometrical structure. So whenever ionic compound is formed, it is formed of a definite geometrical structure. Like sodium chloride is ionic, it is crystalline, we can say that. Clear? It is of definite geometrical structure. As I said, it is crystalline in nature. Fine. So when it is of definite geometrical structure, some heat energy is evolved. So the amount of heat energy which is evolved for the formation of 1 mole of ionic compound is known as, what you can say, lattice energy or lattice enthalpy. So higher is the lattice energy or lattice enthalpy, means higher is the energy evolved, less is the energy present in the compound, and more stable is the compound, we can say that. And as a result, the compound is also soluble in water, so to say. Now next is your enthalpy of atomization. What is enthalpy of atomization? When 1 mole of a given substance dissociates into its gaseous atoms, the enthalpy change accompanying the process is called enthalpy of atomization. When 1 mole of a given substance dissociate into its gaseous atoms, the enthalpy change which is accompanying the process, it is called as enthalpy of atomization, which is represented as delta A H naught. The standard enthalpy of atomization. A stands for atomization. Delta A H naught. If I write only delta A H, that means it is enthalpy of atomization. But when I write delta A H naught, it is standard enthalpy of atomization. We can say that. It dissociates when 1 mole of a given substance dissociates into its gaseous atoms. The enthalpy change which accompanies, means the heat change which is accompanied during this particular process, it is called as enthalpy of atomization, so to say. For example, H2 gas gives 2H. H2 gives 2H. 2 atoms of hydrogen I am getting it. That is called enthalpy of atomization, the amount of heat energy which is involved here. Alright, like CH4 gives C plus 4 hydrogen. This is known as enthalpy of atomization. Atom is being formed. Atom. Carbon atom and hydrogen atom. We can say that. Next is enthalpy of ionization. When 1 mole of covalent compound on dissolution in water, got it, splits up to produce ions in the solution, the enthalpy change is called as enthalpy of ionization. When 1 mole of ionic compound, got it, that is ionic compound, or it may be a covalent compound also, like HCl, we can say that. When it dissolves in water, it splits up into its ions. Now, covalent compound will not split up into its ions. In covalent compound, the ionization is going to take place. Alright. In ionic compound, dissociation takes place. Remember the word. And in covalent compound, dissociation does not take place. Ionization takes place. Ions are being formed. So, whatever it is. So, the amount of heat which is involved here during the process of ionization is known as enthalpy of ionization, so to say. We can say that. Alright, so enthalpy of ionization, we can say that this is known as enthalpy of ionization, we can say that. Suppose if it does not ionize, then what is enthalpy of ionization? 0. If it does not ionize, for example, CCl4, it does not, on dissolving in water, it does not ionize. So enthalpy of ionization is 0. Methane, when dissolved in water, does not ionize. So enthalpy of ionization is 0. We can say that, the one which does not ionize. Next is enthalpy of hydrogenation, the amount of heat, energy or energy that takes place when 1 mole of an unsaturated organic compound is completely hydrogenated is known as enthalpy of hydrogenation. Alright, for example, C2H4 plus H2, it gives C2H6. So when 1 mole of ethene is hydrogenated, the amount of energy which is evolved or absorbed, it's known as enthalpy of hydrogenation. We can say that. Again, I repeat, C2H4 plus H2 will give you C2H6. So the amount of heat energy which is generated, whether it is evolved or whether it is absorbed, then that is called as enthalpy of hydrogenation. Got it? That is known as. Now, enthalpy of allotropic transformation. It is the enthalpy change that takes place when 1 mole of one form of allotropic modification changes into another form of allotropic modification. When 1 mole of one form, like when graphite changes into diamond, or white phosphorus changes into red phosphorus, it is an allotropic form. One allotropic form to another. So the amount of heat energy which is being involved, like rhombic sulfur to monoclinic sulfur or monoclinic to rhombic sulfur, we can say that. That is called as enthalpy of allotropic transformation. Similarly, enthalpy of fusion, we can say that. Fusion means heating, melting, we can say that. So, enthalpy of fusion is the enthalpy change accompanied by the transformation when 1 mole of solid substance changes into the liquid. When 1 mole of solid changes into liquid at its melting point is called as enthalpy of fusion. Similarly, if 1 mole of liquid changes into vapor at its boiling point, it is called as enthalpy of vaporization. Simple it is, enthalpy of vaporization. Now, when 1 mole of solid substance changes into gaseous state, alright, at a particular temperature, then what is that called? Enthalpy of sublimation. Got it? But below its melting point. Got it? When the substance sublimes, changes from solid state to gaseous state. Got it? But below its melting point, it has to sublime. So in this way, we have got enthalpy of fusion, we have got enthalpy of vaporization, we have got enthalpy of sublimation. All the statement, it is the same, just one word you just change it. Like enthalpy of fusion, what I said, when the amount of heat energy which is involved, when 1 mole of compound changes into its liquid state, when solid compound changes into its liquid state at its melting point, it's known as enthalpy of fusion. So for vaporization, what will I say? When 1 mole of liquid compound changes into gaseous state, got it, at its boiling point, that is called as enthalpy of vaporization. Clear? In this way. Now coming to the most important law, that is nothing but known as Hess law. After studying all these things, we will come to Hess law, so to say. Hess law. Clear? We can also write Hess law in this way. H-E-S-S apostrophe S also we can write it down. What is the problem? Hess law. So Hess law says that the total amount of heat energy evolved or absorbed in a reaction is the same, whether the reaction takes place in one step or in a number of steps. The total amount of heat energy evolved or absorbed in a chemical reaction is the same, whether the reaction takes place in one step or in a multiple step, in a number of steps, we can say that. See, I mean to say this. For example, I have to convert from A to B. Now this is in one step. This is, you can say, one step. Now I can do A to C, then C to D, and from D to B. So from A to B is delta H. It may be delta H may be positive, delta H may be negative. It may be exothermic or endothermic, whatever it is. The enthalpy change, it is delta H. Now from A to C, it is delta H1. From C to D, it is delta H2. From D to B, it is delta H3. So according to Hess law, it says that del H is equal to del H1 plus del H2 plus del H3. So the heat change is the same whether the reaction is taking place in one step or in several steps. We can say that. That is, we can say that the Hess law. So the application of the Hess law is that the most important application of Hess law is used for the calculation of the heat change. We are using it. Alright, the thermochemical equation can be treated as an algebraic equation. Now, just now we read thermochemical equations. The heat of solution, heat of fusion, heat of vaporization, heat of sublimation, heat of transformation, heat of allotropic transformation, heat of neutralization, heat of solution, heat of reaction, heat of combustion, the different types of heat which is studied. Now this can be used as an algebraic equation and can be used, which can be added, which can be subtracted, which can be multiplied, which can be divided also. And heat change can be calculated. Alright, these equations or these reactions can be added, subtracted, multiplied, divided, whatever it is. It depends. When you solve the question, you come to know what you need to do, whether you need to add or subtract or divide or multiply to get the required equation. So the Hess law, the most important application of Hess law is that we can use the thermochemical equations. It can be treated as an algebraic equations which can be added, subtracted, multiplied and divided to get the required equation, so to say. Alright, when we'll do the numericals upon it, you will come to know. So, in this way, the Hess law can be used to calculate the heat change in a chemical reaction, so to say, the Hess law. Now, in the Hess law, we are having, there is nothing but we are having the bond energy. Now, in all the thermochemical equation, I have said you that the heat change is nothing but heat of the product minus heat of the reactant. Heat of the product minus heat of the reactant in all the thermochemical equations, so to say, in all the thermochemical equation, whether it is heat of combustion, whether it is heat of neutralization, whether it is heat of solution, whether it is heat of transition, anything. Heat of the product minus reactant. Final minus initial. We can say that. Clear? Always. Now, next is we can also calculate the bond energy of the bond enthalpy. But in case of bond energy of the bond enthalpy, the formula is different. Here, the bond energy or bond enthalpy can be calculated by using the formula bond energy of the reactant minus the bond energy of the product. Bond energy of the reactant minus bond energy of the product. Listen carefully what I am saying. Here, the bond energy can be calculated by using the formula bond energy of the reactant minus product, not product minus reactant. Why? Because bond energy is always negative. So, when you do product minus reactant, it may or may not be negative. Alright, because whenever a bond is broken, energy is required. Whenever a new bond is formed, energy is released. Alright, so hence for that particular reason. So the bond energy is the amount of energy released here. Released bond energy. We are saying the amount of energy released. So in release means it has to be negative. Alright, so when 1 mole of bonds are formed from the isolated atoms in the gaseous state, or the amount of energy which is required to dissociate 1 mole of bond present between the atoms in the gaseous molecules. Alright, so again I repeat, bond energy is the amount of energy released when 1 mole of bond is being formed from the isolated atoms in the gaseous state. Isolated atoms in the gaseous state. So hence bond energy is nothing but calculated in this way, bond energy of the reactant minus bond energy of the product. The rest we will see, that is when we will do the numericals. At that time we will see that how to calculate this bond energy, how to calculate the what you can say, the enthalpy of solution, neutralization and all the things. We will see it. The strictly there is no difference between bond energy and the bond enthalpy. Strictly there is no difference, because energy and enthalpy both are same. The only difference is that energy means we need to say internal energy, which is calculated at constant volume, and when we say enthalpy, it means energy calculated, heat calculated at constant pressure. So there is, strictly speaking, bond energy should be delta U naught values. I said you just now to you, and bond enthalpy means delta H naught values. So bond, what you can say, dissociation energies are obtained at 0 Kelvin by spectroscopic method, a method which will be using in higher classes. By that method, it is being calculated. The bond enthalpy are calculated by considering the that is the equations, the chemical equations, by contribution of the heat energies of the chemical equations, we can say that. Clear? So hence we say here bond enthalpies. Otherwise, strictly speaking, there is no difference between bond energy and bond enthalpy, so to say. Thank you.